Before we go to multiple slit diffraction example, okay, I'm going to revise back what multiple slit diffraction produce. So multiple slit diffraction actually produces interference pattern. So basically the equation will be exactly the same as interference pattern for Young's double slit, where the constructive interference equation will be 2t is equals to m lambda, that is for thin film, which will be d sine theta is equals to m lambda, okay, whereas for the destructive interference, okay, the equation will be d sine theta is equals to m plus half lambda. And of course, we would have the distance between fringes, which is x is equal to m lambda L over t. Or if you want to find the adjacent distance between fringes, that will be x is equal to lambda L over t. So exactly the same equation as Young's double slit. So multiple slit diffraction is a bit easier because it's similar to interference. It's just how they are produced that is different from the Young's double slit experiment. Okay, so let's do an example here. Determine the angular position. Angular position means they want the value in theta of the first and second order maxima for light of wavelength 400 nanometer and 700 nanometer. Now, if it is similar to interference in Young's double slit, the order also follows interference in Young's double slit. Meaning, for constructive interference, okay, if let's say they want the fifth bright fringe of fifth maxima, your order will be 5. But if they want the fifth dark fringe of fifth minima, you have to minus 1. So your m will be 4. Same. Exactly the same as Young's double slit. Okay, so take out all the values, okay, and one m is equals to 1 and m is equals to 2 because it's for maxima. Alright, so we have lambda 1 here, we have lambda 2 here, and we have ratings of 10,000 lines per centimeter. Okay, so meaning your number of slits are 10,000 lines per centimeter. Always convert to SI unit. So if you want to convert this, you want to get rid of the centimeter. Okay, so 100 centimeter is equivalent to 1 meter. Cancel out. Okay, calculate this. You will get 10,000 times 100, which is 1 times 10 to the power of 6 lines per meter. Okay, but this is just the n. We haven't gotten the d yet. So calculate the d, which is the distance between slit, which is 1 over n. So 1 divided by 1 times 10 to the power of 6. You will get 1 times 10 to the power of negative 6. Okay, meter. So that will be your d, the one that we are going to use inside the equation. Right? Okay, so let's continue with the equation. We know for maxima or for constructive interference, use d sine theta is equals to m lambda. Let's calculate for 400 nanometer wavelength first. Your lambda 1 here. Okay. So theta is equivalent to your m is 1 first order. Your lambda is 400 nanometer. Okay, you divide by your d, which is 1 times 10 to the power of negative 6. We'll get 23.58 degree. Okay, so this is your theta at the first order for 400 nanometer wavelength. Okay, so calculate for second order then. So d sine theta is equal to m lambda. Your m is 2. Your wavelength is 400 nanometer. And your d will be 1 times 10 to the power negative 6. We divide by d. Okay. You will get theta 2 as 53.13 degree. Okay, so these are the answers for 400 nanometer. I want you to find the theta 1 and theta 2 for the first and second order of the 700 nanometer light. You should get the answer of 44.43 degree for the first angle. The second one, go and find it yourself, and then we'll discuss the answer later. Okay, so please do this exercise as well. Okay, you can check the answers there. Okay, good luck on that. And I'll go briefly into spectrometer and spectroscopy. If you have the time, go through spectrometer or spectroscopy mechanism in YouTube, or how they use the spectrometer. So usually spectrometer is used to find the wavelength of light. Okay, exactly as the experiment that we were supposed to do, or what we have done. So usually they would put a prism on top of the there's a platform actually here. Okay, so how does the spectrometer looks like? Spectrometer has a telescope where you are going to see where you are going to view the light passing through, and we have the collimator. Collimator is where the light source comes in. There's actually a platform here where you can put a prism or any other medium where the light can pass through. So from there they can measure the wavelength either using calculation, and they will take the angles of refraction or reflection of light. Okay, so that's how spectrometer and spectroscopy work. So at an angle theta, corresponding to the refraction peak of wavelength emitted by the source, a line will be seen. So this line can be a white line, or it can also be a rainbow color line depending on the light source that you use. It can also be determined to a high accuracy using lambda is equals to d over m sine theta. Or you can use any other equation. You can also refer to the lab manual for experiment 2. Okay, so the narrower the slit, okay, meaning the smaller opening of slit for the light coming in, the narrower but dimmer the line is, depending on the size of the slit. It can also be used to identify atoms or molecules. Okay, when a gas is heated or large electric current is passed through, gas emits a characteristic line spectrum. So it only occurs at high temperature and low pressure. So there's many useful or many purpose of using the spectrometer. I want you to go through it, okay, and understand the mechanism behind it.